Okay, so what we're doing here is we're pumping water. We see we have this valve off. This is the mains water coming in, and we're pumping this water up to above the pressure of the heating system. And the reason that we're doing that is because we want to see if there's a leak in this pipe, and this pipe goes into a coil in this thermal store. It comes back out from this pipe that says hot water out, and then it comes into this thermal store, and then it comes out, and it comes out here from this pipe here. Now I will do a quick drawing of how that looks, just drawn out on a sheet of paper. But what is happening is the water, the pressure is dropping right the way down until it meets the same pressure as the heating system. So the water that we're pumping in here is leaking from these coils of pipe and pushing back into the heating system. Now potentially, if the heating system had more pressure than the cold water coming into these coils, it would go the other way. So in that case, you would get central heating water into your hot water taps and showers. And that's what happened when we isolated this system before. That's why the taps run so dark. And now you can see this pressure is dropping. So give this 5 minutes and this will drop right the way down to 2 bar. So it's just a gradual drop of pressure, indicating that there is a pinhole or a crack on the weld of the coil. So you can just see, there it goes. And give this about 5 minutes and it settles at about 2 bar. This coil is actually okay, because if we valve this coil off, it holds pressure, so this coil is actually still in okay shape. It's this one that has gone. So here is that simplified sketch I've made of the plant room. We have 2 floor standing Worcester Bosch oil fired boilers, and we have 2 of these thermal stores. I've just drawn one just so I can explain this in layman's terms easier. The purpose of the boilers is to charge these thermal stores. These are sometimes also referred to as buffers. It's designed to be filled with very hot water, so we have 80-degree water being pumped in from the boilers, which is returning probably with around a 15-20 degree Celsius temperature drop. Depends on how much usage is being taken, how much energy is being drawn from the thermal store. A good way to think of a thermal store is a battery, a rechargeable battery. So it's storing energy, the boilers are piling the energy in, and then as the energy is being pulled off, we have a glut of energy to give us a store, as the name implies. Now off of this thermal store are tappings like I've drawn, and these tappings will run off to radiators and air handling units, heat emitters all around the house, and then that will be then pumped back. All of those circulators that are in the top left hand side of the pump room, they're pulling water from these stores and they're running it around the house, and then they're returning it back in here where it can be sucked back into the boiler and be reheated. In the winter, the boilers are probably running 15 to 18 hours a day to try and keep up with the temperature loss that's occurring in these stores. In the summer months, when nothing else is being tapped from this, the boilers will run, heat this store up to about 80 degrees, then the thermostat will be satisfied, and then the boiler will shut off. Until that is, a hot tap is run. Now this is a hot tap being run here, and then you can see the water's coming out about 60 degrees Celsius. What happens when a hot tap is run is cold water from the booster set that is in the adjacent plant room enters a tapping on the side of the thermal store, and then inside the thermal store is a coil of pipe. Now I've drawn this as a copper coil of pipe. It's more likely to be a stainless steel pipe, and that is impossible for us to see because this is a welded encapsulated store, and this coil of pipe is inside the store. There are actually 2 coils, they're twin coil units at Newark Park. And the cold water comes in here and it runs around this pipe, and obviously that's a big length of pipe in a small space because it's coiled around in a loop, and it's picking up the heat from this 80-degree water, and by the time it comes out of here, it's practically at the same temperature as the surrounding water. It will be between 75 and 80 degrees, and we can see that on some gauges on the side, that it's coming out very, very warm. It then hits this thing, which is the horn valve. Again, this has various names, TMV3 or TMV2, temperature mixing valve, tempering valve, some people call that. The purpose of this valve is to mix some cold water in with this very hot water and give a safe and stable output temperature of the water that is going to reach the hot taps and the showers. Now, it so happens I've made another video about how this valve is not correctly installed in the plant room, which I've made available because this cold pipe is undersized, so it can't ever get enough cold water, but that's in another video. So let's imagine everything's working and then the water comes out at 60 degrees Celsius. Obviously, this cold water running through this coil of pipe cools off the store, and so the boilers will fire and they'll keep the water up to around 80 degrees, meaning you can continue to run hot water. So this setup allows for a very, very high flow rate of hot water because you can run this water very quickly around these coils and out it shoots at 60 degrees Celsius, picking up the heat from the 2,000 litres of very hot water that are surrounding it. Not necessarily the most efficient way of producing hot water because in the summer months you're storing a lot of water, but it's a very, very good way of providing lots of hot water in a peak demand situation. Now, what we know is that the coil in one of the thermal stores has got a leak in it. That could be a pinhole, it could be a crack, it could be a crack in the weld internally. That we don't know, but what we have proven is that there is a leak. And as I explained in the other video, how we know that is because we have increased the pressure of the we isolated this so there was no water coming in, and we increased the pressure in this with this capped off to above the pressure of the heating system. Now the pressure of the heating system is around 2 bar pressure. It's running at around 2 bar, and once we increased this pressure, we increased it to about 6 bar, and then we watched a gauge and we watched it creep down until it reached the operating pressure of the heating system, which is 2 bar. And so, but what we're proving is that the water that we're pushing into here is leaking out internally until it marries up with the working pressure of the heating system. So that categorically proves that this coil has got a leak. What's quite crucial to remember, and what it is occurring, have led us to suspect that there was an issue, was this valve on the top. Now that's why I've written 3 bar. On the top of both of the thermal stores there is a pressure relief valve, and the purpose of that valve is if the pressure gets above 3 bar, which is above the pressure that this boiler is rated for, it's above a safe pressure for radiators to reach. It's just a industry sort of standard for domestic systems that we don't run heating systems above 3 bar. What happens is there is a washer on the top of this valve, a washer and a spring, and that will lift up and water will sometimes shoot out, sometimes dribble out. It will release and it goes down to a drain. The pressure relief valves at Newark Park are dripping and have been dripping for a little while, and actually it was noted on my first visit and flagged up as something that we had to investigate. But that alone didn't indicate that there was an issue with the coil. But just so I can explain what's happening, we've got 6 bar pressure coming in here. If no outlets are run, particularly overnight, but I would imagine that there are often times where there are no hot outlets run, the pressure in here will be slowly spilling out because it's not a huge leak, it's not completely ruptured, but that pressure will be coming out at 6 bar, over pressurizing this, and so this 3 bar pressure relief valve opens up and lets some water off. Now I've got a video that I made in 22 when I said we need to figure out what's going on with this pressure relief valve. What actually led us to realize that there was a problem with the coil is there was a leak on this connection outside of the thermal store on a union where the external pipework joined to the side of the thermal store to the coil. And when we repaired that union, we shut this water off and we drained the water out. We drained the water out here at this tapping, and it kept dripping constantly, and so instantly we were suspicious that there was an issue. And why it was dripping constantly is because this 2-bar pressure of the heating water was pushing into the coil and coming out and filling up the coil with this water that's on the outside that is normally reserved for the heating system and the boiler. That was pushing into the coil. And so what then happened, once we made our repair to this external joint and we run the hot taps, the water that came from here and run out of the hot taps was very, very mucky. It was, it marked the baths, and it was a greasy, what we call primary water. Primary water is the water that's in the boiler. It was clearly primary water with iron in it from being in this thermal store. So we had, and I'll show a picture of the pressure relief valve, which is still now dripping to this day. And I'll put a video up of the water and some pictures up of the water that we had running off from the taps after we made this repair. In fact, I'll do that video now. And so the reason that we don't have immediate cause for alarm is because this water that's coming into the coil is running at a higher pressure. It's contaminating the heating water. Now, if the heating water was running at a higher pressure than the inlet, I'd be more immediately concerned, because then you would be constantly showering and washing in water that is in the central heating system. However, even with this being the better of the two possible scenarios, we still must address this issue. And we must address it because we are constantly filling the heating system with fresh mains water, and fresh mains water contains lots of dissolved oxygen, and that dissolved oxygen will lead to accelerated corrosion. The reason that we have sealed heating systems is to prevent oxygen integration, because we know that we need oxygen as part of that rusting process. And so this fresh water that's pushing in and then dripping out from here would be contaminating any corrosion inhibitor. Not that I think there's any corrosion inhibitor in the system at the moment, but it will also be causing corrosion, and that in turn will cause magnetite, which is a magnetic slime that's produced when you get too much oxygen in central heating primary water, and that will damage components within the heating system, mainly circulators, but also valves and other components. So it's imperative that we deal with this. Now, as I've mentioned, this coil is integral to the thermal store, so removing the coil and repairing it is not possible. You'd have to cut the lid off of the thermal store and climb in there and find where it's leaking and do repair. It's just not practical. But there is a setup where we can abandon this coil, and instead we can use spare tappings, which there are spare tappings on the store, to run round a plate heat exchanger. Now, I've got some images to show that, and then we can show you a plate loading kit, and you can use this plate loading kit to produce just as much hot water using the energy that's in the thermal store, but with a component that lives externally. So you can actually buy thermal stores with the plate loading kit already bolted on the side, but I think we're going to have to buy a third-party unit to deal with this problem. Alternatively, we would have to take out the thermal store, or stores, because if one is broken the other may be shortly behind it, and then we would have to replace both thermal stores. And here we have a photo of a packaged plate heat exchanger. So plate heat exchangers are used in every combi boiler manufactured on the planet today, and they can be used for much bigger properties as well, because the principle is to stack these plate heat exchangers, these plates that have turbulence channels on them to turbulate the water and increase the surface area, and these are stacked, as you can see in this video, to create a very large surface area. They're obviously made per application, and then once that's all bound together with these bolts and these gaskets, that it's watertight. Now you can get brazed versions of these, which is what you find in combi boilers, but for most purposes that are commercial you get this type, which have these individual plates. And then the fluid is run, and as you can see in this animation, the water hits every other plate. So this could be the cold water running in, and then on the alternative plates we'd have the water from the thermal stores, which is hot water. And the two waters never mix, but obviously because they're in close proximity and they're stainless steel plates, they conduct the heat. So the cold water that's pumped in ends up coming out very hot, and then it would go into the tempering valve, the TMV valve, and have the temperature reduced back down to 65. I mean, you can get some of these units that they have a pump that modulates the speed of the water through the plate heat exchanger to moderate the heat, but that's overly complicated for this application. As I mentioned, they come in all shapes and sizes. You can see here from huge commercial and industrial units, and you'll also find them in every little combi boiler in the country or on the planet, and they'll be inside as a little brazed unit. And so a packaged or plate loading kit, as we see here, will be a very good solution. You can see that you can get them ready attached to thermal stores. They're serviceable. We can work with the existing thermal stores, so we'll keep costs down. And we've used them previously to great success. We've had units that will produce 150 litres per minute, and you can get much more powerful units than that. So we just need to specify the right unit, clear the space for it in the corner of the plant room, and that will provide domestic hot water at the same performance as the existing setup, without any contamination of the heating system or inadvertently contamination of the domestic hot water system. I hope this has been useful to explain the issue, and I'm sure we'll discuss it further once you've digested this information. Thank you very much.